Hi, today we're going to be looking at the 2015 PAT paper and going through question 16. So question 16 is a question involving a collision. A ball of mass 2 kilograms slides along a frictionless smooth surface at 1 meters per second and collides elastically with a stationary ball of mass 1 kilogram. And we're asked to find the speeds of the balls after the collision. Now, when thinking about collision questions, the most important thing to remember is the conservation of momentum. Momentum is always conserved in any collision between objects. So we can use that to get expressions relating the velocities before and the velocities after the collision. Also, in this case, we're told that the energy is conserved because the collision is elastic. So this means that kinetic energy before the collision and kinetic energy after the collision will be equal. So we can equate those two and have another equation. And we can use these two equations to solve for our variables, speed of each ball after the collision. So let's start by drawing a diagram. So before the collision, we have a ball of mass 2 kilograms travelling at 1 meters per second and a ball of 1 kilogram, mass 1 kilogram, stationary. And afterwards, we have the ball of mass 2 kilograms moving at a speed v1 and the ball of mass 1 kilogram moving at a speed v2. We'll arbitrarily point the directions to the right and the signs will come out positive or negative accordingly, and that'll tell us the direction of their motion. So let's start with momentum. So we know that momentum before momentum before will be equal to the momentum after. Well, our momentum is, as we know, mass times velocity. So before, we have the ball of mass 2 kilograms moving at 1 meters per second, but the ball of mass 1 kilogram is stationary. So this ball here has absolutely no momentum. So the only momentum we have before is the momentum of the motion of the 2 kilogram ball. However, afterwards, we have both balls moving. So we have momentum coming from both objects. So let's write that down. So before we have momentum of 2 times 1, 2, being equal to the momentum of the ball of mass 2 kilograms, 2 v1, plus the momentum of the ball of mass 1 kilogram, plus v1. We also have energy before is equal to the energy after, because the collision is elastic. Well, again, we have this object being stationary, and the only energy we'll consider in this collision is kinetic, as they're saying the balls are moving on the same plane, so there's no change in potential energy, and the balls don't have any elastic energy. So we only consider kinetic. Now, as this ball is stationary, it clearly has a kinetic energy of 0. So we only consider the kinetic energy of this ball of mass 2 kilograms. So that means we have half times the mass times the velocity squared is equal to, well, afterwards we have half times 2 times v1 squared plus half times 1 times v2 squared. Simplifying, we get that 1 equals v1 squared plus half v2 squared, or we can multiply through by 2 to give us that 2 equals v1 squared, 2v1 squared plus v2 squared. Now, let's label these equations 1 and 2. Notice from equation 1 that 1 gives us that v1 equals 2 into 1 minus, v2 equals 2 into 1 minus v1. There should be a v2 up here. So we can substitute, if I can spell the word substitute, sorry about that. Substitute this into equation 2. So what we're going to do here is we're going to replace our v2 in equation 2 with our expression for v2 from the equation 1. So doing that, we get 2 equals 2v1 squared plus, well, v2 squared is going to be 2 squared, 4, into 1 minus v1 squared, which we know, well, 1 minus v1 squared will be v1 squared minus 2v1 plus 1. Dividing through by 2 and expanding out, we get 1 equals v1 squared plus 2v1 squared minus 4v1 plus 2. So we've got a 2 on the outside here when we divide through by the 2. So 2 times v1, 2 times minus 2, 2 times 1. Bringing it all together, we get, sorry, that should be squared. We get 3v1 squared minus 4v1. And we're going to bring the 1 over here to give us a plus 1 equals 0. Now notice this factors to give us 3 into, so 3v1 minus 1 multiplied by v1 minus 1 equals 0, which tells us that v1 equals 1/3 meters per second or 1 meter per second. Let's now find the corresponding values of v2 for each value of v1. So let's go when v1 equals 1/3 of a meter per second. We can substitute that into our equation 1 to give us 2 equals 2 times 1/3 plus v2, which tells us that v2 equals 4/3 meters per second. And we can substitute so this is for 1/3. And then 1 tells us that 2 equals 2 times 1 plus v2, which tells us v2 in fact would be 0 meters per second. Now let's think about this. If we have the velocity of v1 afterwards being 1 meters per second, this corresponds to the velocity of v2 being 0 meters per second. So think about this intuitively. This means that this ball here has collided at a speed of 1 meters per second, so the speed we're going to give it afterwards, with a stationary ball, and then has the same speed afterwards, but the stationary ball is still stationary. So if you can picture that, what that would mean is this ball has essentially passed through this first ball, leaving this stationary and this carrying on at the same speed. Clearly this cannot happen, so we have to reject this result, which tells us our final answer is going to be v1 equals 1/3 meters per second and v2 equals 1 meters per second. Now there is another way to go about doing this question. If you've watched our video on the coefficient of restitution, you can use that to solve this question. So as the collision is elastic, we know that the coefficient of restitution is of value 1. Remember, our coefficient of restitution, E, is defined as the speed of separation over the speed of approach of the two colliding objects. So let's quickly redraw our situation. So here's our diagram. Now let's think. Our coefficient of restitution is of value 1 because it's elastic. And let's think about our speed of separation and our speed of approach. So our speed of separation is going to be the difference between these two velocities as they're going in the same direction. So let's just say that it's going to be v2 minus v1, because we're not sure at this moment if v1 is bigger than v2, and the negative sign will sort itself out. So we write down that 1, our value of E, equals our speed of separation, v2 over v1, over, well, our speed of approach is going to be, well, this is at 0, and this is at 1. So it's going to be 1 minus 0, or simply 1. So we get 1 minus 0, or we get that v2 minus v1 equals 1. So let's write that down here next to our original equation from the conservation of momentum. We'll call this equation 3. We can now solve these simultaneously. If we multiply equation 3 by 2, we get 2v2 minus 2v1 equals 2, and we can call this equation 4. We can then add equation 4 to equation 1, which will give us that 3v2 equals 4. Implying v2 equals 4/3 meters per second, as we got before. We can then use equation 3 to get our result for v1. So v1, so 3, tells us, equals to v2 minus 1, which is 4/3 minus 1, which is 1/3 meters per second. So we see the two methods give us exactly the same results. And arguably, the method of using the coefficient of restitution is considerably faster than the energy equation, because you don't have to consider the two cases when you solve the quadratic. And that's the end of this question.